Okay, thank you again for being here. Before introducing our speakers of today, I would like to pay a tribute to the late Victor Venema, because he is the one who started this series of colloquia. This is the first without him. And, in his memory and in the memory of the contributions, of his contributions in the homogenization community, I hope that we'll be able to continue this colloquia also in the future. So today I'm very happy to announce as speakers Mrs. Beatrix Izsák. She'll be presenting, the title of her presentation is Testing the New Version of MASH version 4.01 for Homogenization of Standard Deviation. Her co-author is someone that everybody knows in the homogenization community, Tamás Szentimrey. Beatrix, I'm sorry if I made any mistakes in pronouncing your name. Thank you very much. Well, for those who do not know me, I'm Tamás Szentimrey. I'm professor of atmospheric physics at the Laboratory of University of Physics in the University of Patras of Greece. And our next speaker will be Miss Ninh Nguyen, and I'll give you the title of her talk later on. So, dear Beatrix, thank you. And the floor is yours. You can start sharing your slides.
And you can see it.
Yes, we can see it and we can hear you.
Okay, but first, my name is Beatrix Izsák. I work in the climate research department of Hungaromet. Hungaromet is the new name from the Hungarian Meteorological Service. In this climate research department, we homogenize our data series every year using the MESH software. In this presentation, I would like to present the results of my first application of MESH 4. The earlier version of MESH method were developed for homogenization of daily and monthly data series in mean. The software was developed as an interactive artificial intelligence system that simulates the human intelligence and mimics the human analysis on the basis of advanced mathematics. The new MESH version, MESH 4, is able to homogenize also the standard deviation. The problem of standard deviation is related to the monthly and daily data series homogenization. And the MESH 4 includes the procedures of earlier version, MESH 3. Both of these two software, MESH 4 and 3, you can download free from the homepage of the Hungarian Meteorological Service. The main properties of the version MESH 3, in case of monthly homogenization of monthly series, it is a relative homogeneity test procedure based on hypothesis testing. It's a step-by-step iteration procedure, and you can choose between additive or multiplicative model. It's depending on the probability distribution of the climatological element. It includes quality control and missing data completion. It provides the homogeneity of seasonal and annual series as well, and the metadata can be used automatically. The homogenization results can be evaluated on the basis of verification tables. These tables generated automatically during the procedure. And in the homogenization of daily series, the main properties is the procedure is based on the detected monthly inhomogeneities, and it includes quality control and completion of missing data in daily data too. The new version, Mesh 4, has been developed for homogenization of daily and monthly series, but the most important novelty of this version is the homogenization in standard deviation beside the mean. The basic concept of mesh system is first to homogenize the monthly series, derive it from the daily series, and then to homogenize the daily series based on the detected monthly inhomogeneities. Something about the mathematical basis, the theoretical background of homogenization. Let us assume that we have, for example, monthly data series, Y1T series, the new observing series, and Y2 series, the old observing series. And we have, for example, a T breakpoint, and before the T time, the Y2 series can be used, and after the T breakpoint, the Y1T series can be used. We have the theoretical cumulative distribution functions, and the difficulty in homogenization that these functions change in time. And if the two probability distribution function not equal, then the merged series is inhomogeneous. And we have to homogenize the Y2 series with this transfer, using this transfer function. And in case of normal distribution, it's a special case, but this is very common in meteorology. Let us assume that we have the Y1 and Y2 series. Both are normally distributed with the the notation of E is the mean value and D is the standard deviation. And then the transfer function of homogenization, we can calculate with this formula. This is a simple linear function and nothing with the Tate distribution extreme function. And the other remark is you can see that only the mean and the standard deviation must be homogenized in case of normal distribution. The relation of daily and monthly homogenization. If we have daily series, the general way is the calculation of monthly series. And after homogenization of monthly series, very important to know because of the larger signal to noise ratio. And after homogenization of daily series based on monthly inhomogeneities. And the natural question, how can we use the valuable information of estimated monthly inhomogeneities for daily data homogenization? What is the practice for daily series? For example, when we homogenizing the monthly mean series, the popular procedure is breakpoint detection, adjustments of mean, and assumption homogeneity of higher order moments. But in case of homogenization of daily series, attempt or try to homogenize also the higher order moments. And the use of monthly information is only the detected breakpoints. And there is a contradiction. It can be proved when some inhomogeneity in mean and the standard deviation in case of daily series, then it can be proved that there are inhomogeneity in monthly values. And the question, why are the monthly adjustment factors not used for daily homogenization? The problem of inhomogeneity of the standard deviation. This is a theorem. The notation, we have daily data YT series, and we can calculate the average of the daily values, the monthly VM values. And we calculate the S series, monthly variable for examination of standard deviation. And we have daily data, and there is inhomogeneity in mean and in standard deviation. Then we can calculate the appropriate monthly variables, the average Y series and the S series for monthly variables. And then it can be proved that the monthly mean is also inhomogeneous in mean and in standard deviation with the same measure. And moreover, this S series can be used to estimate the inhomogeneity of standard deviation. This is the two statement, and after we can these steps in mesh, build in mesh, or theoretically steps to homogenize the daily series. The first step is homogenization of monthly series, the S and the Y, the average of the Y mean series. The first is homogenization of S series by multiplicative model, breakpoint detection, estimation of inhomogeneity of standard deviation. And then adjustment of standard deviation of the average Y, the monthly Y series. And the next step is homogenization of adjusted Y series by additive model, breakpoint detection, estimation of the inhomogeneity of mean. And then we can make the adjustment of means of the Y series. And there is an assumption that homogeneity in higher order moments, and in case of normal distribution, it is always right. And the next step is homogenization of daily series. Homogenization of mean and standard deviation on the basis of the monthly results. The used monthly information are the breakpoints and the monthly adjustments of the mean and standard deviation. And when the daily data are normally distributed, there is no inhomogeneity in the higher order moments. You can read more about in these two publications of Tamás Szentimrey. And the summary of mesh software. The mesh is based on homogenization of monthly series derived from daily series. The procedures depends on the distribution of climate elements. And in case of quasi-normal distribution, as I mentioned, beside the mean series, another type of monthly series is also derived to estimate the inhomogeneity of standard deviation. That was the S series. These series are homogenized in standard deviation by multiplicative model. The monthly mean series adjusted with the estimated inhomogeneity of standard deviation and are homogenized by additive model in mean. And in case of quasi-log normal distribution, for example, precipitation, the monthly sum series are homogenized by multiplicative model. And summary of the mesh 4 system looks like the mesh 3. The main properties, the difference is in bold, homogenization in mean and in standard deviation in case of monthly series, and in daily series to the homogenization in standard deviation. And some verification results for homogenization of mean and standard deviation. We used 27 stations data series from Hungary from 1901 to 2023 daily mean temperature values. As I mentioned, a very strong quality control built in mesh 3 and 4 too. And error file generated automatically while mesh is running. And this is an example I could from the error file. Of course, the file is bigger, but there is at the end of the file a summary. number of days with error, total number of errors, and the maximum minimum error. And you can see that the element temperature values contain large errors. And the verification statistics in MESH, the test statistics generated automatically during the procedure. For example, very important to know the test statistics for series in homogeneity. For example, before and after homogenization, the relative modification of series, or the representativity of station network, or the evaluation of metadata. And the first results on the left graph is the inhomogeneity in mean, the average of the 27 stations value. The dark blue bar represents the test statistics before homogenization, and the light blue bars for test statistics after homogenization. And there is the inhomogeneity in standard deviation with the same dark blue and light blue bars. In both cases, inhomogeneities are larger in the summer semester than in the winter semester. And I choose 3 case studies. The first one is a big city in Hungary, Pécs, geographical location here in South Hungary. There is the estimated inhomogeneity mean, and there is the estimated inhomogeneity in standard deviation. There are always the annual mean values. The black one is for the before homogenization, the raw station data series, and the red one is for the homogenized data series. And here is some notation. There was a missing data replacement and relocation to the airport. Before the relocation to the airport, the measure, the observation site was in the city center, and relocated to the outskirts because of the airport, and there was some measurement change in time. You can see here the metadata from the database. Here is the name of the station, and the dark blue means the replacing the missing value. Here is quite good, the metadata, but incomplete for many other stations. Here you can see here first one, the beginning of the measure in this place, and the end of the measurement. And here is the type of the meteorological station. For example, K3 means that 3 times measurement per day, K8, 8 times, S a synoptical weather station, first with 24 hourly measurement, and after, when the automatic weather station is there, then the 10-minute measurement. And you can see here some detected breakpoints. And the second case study is in Zabar. It's a very special station in Hungary, a little village near to the Slovakian border, the coldest place in Hungary. The most of the daily minimum extreme measured here. And when you look at the inhomogeneity mean, the inhomogeneity in standard deviation, the annual mean series, and the annual standard deviation series, looks like that in 1999 something happened. And here is the metadata that the measure, the beginning in this place, Zabar, beginning was only in 1999. The previous measurement were 2 valleys further away. In Salgótarján, this is bigger. This is a city, and Zabar is a little village. And you can see here as a basin or a valley, and Zabar is a basin or a pool in the pool, and cold air confluences here. And it's very important to know the long data series. We merged these 2 data series, and there is the methodological change K 3 times measurement 4 times, and I don't understand 15 years long was only maximum and minimum temperature measurement. The daily average is only the average of the daily maximum and minimum temperature. And after in Zabar as automatic weather station, this is the 10 minutes measurement. And there is the biggest, the difference between the raw and the homogenized data series, of course. And the third case study is Budapest. Budapest, we are here in the headquarters of the Hungarian Meteorological Service. Here is some notification of the detected change point, something that we found in the metadata, some breakpoint, but I think there is no complete, because here we are here and in this building, and the weather station is on the roof of the building, but earlier was in the garden. And you can see here the estimated inhomogeneity in standard deviation and the inhomogeneity in mean. And here you can see some inhomogeneity, and here is the 2 satellite picture. You can see here there was a large construction site for years, and dark brown mounds of ground replaced with this green areas of bush and woodland, and this caused this inhomogeneity. But in case of maximum temperature, it is bigger. And in the new version of MESH 4, we have 2 new verification statistics. Some special verification tables also can be used with statistics to characterize the estimated inhomogeneities. The first one is statistics for inhomogeneity in mean. This statistics, we can calculate the different the mean values before and after homogenization, and of course this is the average of this value. And the statistics for inhomogeneity and standard deviation is the ratio of the standard deviation before and after homogenization. And the estimated inhomogeneities for mean. This is the result for the all 27 stations and the average. The highest inhomogeneity is in summer and the lowest in January. And the second new statistics estimated the inhomogeneities for standard deviation. Also, in the case of standard deviation, summer values are the highest, and the winter values the least inhomogeneous in case of standard deviation. And some meteorology, climate change detection or trend estimation. We publicated many times that the average temperature trends show a significant increase in Hungary. You can see here the seasonal values, the annual value, the spatial distribution of the trend values. Here is the homogenized, the red line, the homogenized spatial mean of annual mean series, and the black one is the raw data series. And the dark blue line is the linear trend, the estimated linear trend line. And this change is significant, the whole area of Hungary. And what about the variance? What about the standard deviation? I asked my colleagues, not from the climate research department, the forecaster people, the modeling, numerical modeling people, and the others, and 90% said to me that it's significant increase in standard deviation too. But here is the result. The change in the annual mean of monthly standard deviation per station. We detected significant decreasing trends. Except this, there is no significant change. This is Zabar station or coldest place, and another is Nagykanizsa is in West Hungary. But the other weather stations, significant decreasing trend that's detected. And this is the annual mean of monthly standard deviation, the station mean of the 27 stations. The black line is for the raw standard deviation series, and the red line is for the homogenized data series. And the blue line is the estimated exponential trend. And this decreasing trend, the change is significant. And the summary, raw temperature data series are highly inhomogeneous, not only in expected value, but also in standard deviation. In the case of the Hungarian data series, the change is values fluctuate around higher values with smaller standard deviations. And in order to use mesh4 and evaluate the results, it is very important to know its mathematical background. And thank you for your attention.
Okay. Thank you very much, Beatrix, for your excellent presentation. You conveyed very important information. Well, MASH is a valuable tool for the community, so as far as I understood, this version is even more improved. Are there any questions from the audience, please? You can either switch on your microphone and speak directly, or use the hand in the reactions button. I can't see any hands lifted, so I don't see anybody wanting to ask something. Beatrix, I have a few questions, if I may. The first question is, when you homogenize daily data with the new version of MASH, is there any kind of pre-processing required? For instance, the monthly data are calculated automatically by the software, or we have to provide?
Calculated automatically. As was earlier in the mesh 3, you can it's calculated, and there is in the manual. It's downloaded on the homepage of the Hungarian Meteorological Service. Another automatic algorithm for mesh 4, but as I mentioned, maybe the background is important, but not so. So you can try to use this new software. There is an automatic algorithm in the manual.
But in this calculation of averages, monthly averages, you take into account the 5-3 rule of the WMO regarding the missing values, or it is just a numerical average of
this S values, or I don't understand the question.
No,
To calculating the standard deviation values, or
no. I mean, when you calculate the monthly averages, you can't calculate an average if you have more than 5 missing observations or
yes.
3 consecutive observations. So has this been taken into account?
That can answer maybe Tamás, but I think it's built in the mesh.
Yes. Yes. According to the WMO rules, are calculated to the monthly values from the daily values. So we take into the number of missing values.
Okay.
And if there are too much missing values, missing daily values, then the monthly value will be a missing value also.
Okay, great. Thank you very much, Tamás. As far as I understood, the software, the new version is downloadable from the webpage of the Hungarian Meteorological Service. Okay, maybe Monica, can you enter this link to the chat for all the participants to have it? I suppose that there is also an English version of the software, because I saw some of your screenshots in Hungarian, but I suppose there's a language option.
I think this is in English.
Because I saw some of the screenshots that you have shown before in your presentation, everything was in Hungarian, or it was from another software. Did I?
That was no. The mesh is always only in English.
Okay, great. Thank you. Well, this will be all from my side. I have a question on the chat from Ms. Melita Persic-Tajic. If I pronounce it correctly, apologies if I'm wrong. The question is, what about the fixed number of days in a month? It was 30 in the equations.
I don't understand, because the fixed number, as Tamás mentioned, that is, as the VMO said, that when 5 days or 10 days missing value, then the monthly value missing value. Or I don't understand what is Melita's question. Maybe I can read on the chat. Fix the number of days in a month. It was, sorry, it's of course calculated with the exact day with the month, not only with 13. In case of February, for example, 28, in December 31. Okay, I understand.
Okay, thank you. Ms. Tadic, are you covered with the? Yeah, okay. I have another question from Ninh Nguyen. The question is, could you explain more about the correction procedure of the daily series from the segmentation results of monthly series? You can see the question on the chart.
There is everything in the verification statistics, and there is no time. But when it's too much now to share all the verification tables, but there is everything. I like the mesh software because so many verification statistics there, and I knows in every homogenization what we made with the data series.
Okay, thank you very much, Beatrix. Thank you, Monica. Monica Lakatos has entered in the chat the link where you can download the software from the web page of the Hungarian Meteorological Service. Thank you very much. If there are no other questions on the first talk, I would like to invite to the floor Ms. Ninh Nguyen. The title of her presentation is Homogenization of GNSS Integrated Water Vapor, Time Series and Estimation of Climatic Trends. The co-authors of this presentation is Professor Olivier Bock and Professor Emilie Lebarbier from Paris, France. I had the opportunity to, I know this work because I had the opportunity to be, to act as a member of Ms. Ning's PhD thesis last December. It's an excellent work. I hope that you will enjoy it. Ning, the floor is yours. Thank you for being here with us this afternoon.
Thank you, Thanos. Thank you for your invitation. Can you hear me?
Yeah, well, if you can speak a bit louder, it would be nice. Thank you. Yeah, now it's perfect.
Now I'll share my screen. Can you see?
Yeah, everything is crystal clear. Thank you.
Thank you. Thank you, and hi everyone. My name is Ninh, and I'm very happy to be here and sharing my work with Dr. Olivier Bock and Emilie Lebarbier about the homogenization of the GNSS integrated water vapor time series and the estimation of the climatic trends. So as I show you here in this figure, you can see that we have the relative trend of the total column of water vapor or the integrated water vapor from the two different data sets, the ERA 5 reanalysis shown by the map and the GNSS data illustrated by dot. And there's 2 points I want to say here about this figure is that first, you will see the main part are in blue. So it indicates the positive trend in the water vapor over the world. However, we also see some drying spots like South America or Australia, etc. And the second point I want to say that in many stations of the GNSS, we found a different value on the trend, and the difference in the trend from between the two data sets is because we have some inhomogeneity in the GNSS data. So that's why we focus on the homogenization problem in this study. And with the long-term and high quality of the GNSS dataset, we can monitor better the climate change. Use this to verify the atmospheric reanalysis and climate model, and correct bias in the model simulation and satellite observation. So in this figure, you can see there's really water vapor anomaly from different reanalysis dataset and the GNSS, which is independent observation. And we can see that globally, we have a consistent trend between the different dataset. However, if we see on the map, we can see some difference. And our goal in this study is to get the high quality of the GNSS with the mean bias in the GNSS is about 0.5 kilogram per meter square or lower. With the trend, we hope to have smaller uncertainty of 1% per decade. And to do that, we implement the homogenization at the post-processing level of the GNSS. And here I show you one example of the time series. So this time series in GOP station of the Czech Republic from the ERA 5 reanalysis in red and from the GNSS data in black. And firstly, you can see that the two datasets are quite consistent. The two series are quite consistent and they have high seasonal variation. However, when we see the trend value, they are opposite and have different amplitude. So what we do here is to see the difference between the two series. I plot the time series of the difference, and you can see that there's some inhomogeneity in 2001 and also small inhomogeneity in 2010. The vertical line here illustrates some changes in the GNSS measurement in the antenna or receiver, and they may induce some inhomogeneity in the GNSS data. So as you can see that to homogenize the GNSS data, we don't apply segmentation on the GNSS data, but we apply the segmentation on the difference in order to easier to detect the change point. In my presentation, I will focus on three parts. The first part will focus on the segmentation. We apply the GNSS method on the series GNSS minus the reanalysis, which is a reference. In the second part, I focus on the attribution method, in which we focus to detect where the change point come from. Is this the GNSS or the reference era data? And in this part, I also introduce my package GNSS Edge. And at the end, I would introduce some result on the trend, the impact of the homogenization of the trend. So firstly, let's focus on the GNSS. The GNSS segmentation method models the time series with the piecewise mean, the periodic bias, and the white noise with the monthly variance. And this method, in this method, it estimates all the parameters, including the position of change points, the number of change points, using the penalized maximum likelihood, which is an optimal solution. So the idea behind the GNSS method is that first we estimate the monthly variance in the series, and then the periodic bias function, the position of change point, and the mean of each segment are estimated iteratively with the help of using the dynamic programming. At the end, we estimate the number of the change point using the penalized criterion. So we try to apply the segmentation on the different GNSS generation. And in this table, you will see that we have some statistics on the result. I compared the segmentation result between the report 1 and report 2 in the same time span. And you can see that the second generation have a smaller noise, a little bit smaller noise, and periodic bias function also smaller. And with the smaller noise, the segmentation detect more change point in this data set. And you can see also that there's only about 50% of change point are similar detected between the two data sets. I show you here one interesting example where the segmentation detect 4 change point in the report 1, but 6 change point in the report 2. And interesting point here is that there's unchanged point in the antenna and radome in 2006, and then they changed back again in 2010, and these changes has impact on the report 2 but not in the report 1, and the GNSS is able to detect the difference in the two data sets. The second point I want to draw attention here is that the validation rate when we apply the segmentation on the two different data sets are around 30%. It's implies that we have about 7% of change point detected by segmentation is unknown. And so here I show you one example. The example I showed you previously, the segmentation detect 5 change points. The first 3 change points are close to the metadata in the GNSS data. And it is illustrated by the triangle here. with a different color is the different type of changes. And the last two change points are not validated by the metadata. They are quite far. So we cannot say they are due to the GNSS. It may be due to the reanalysis data, or maybe we're just missing some information in the metadata, or it's just a false detection from the GNSS. So for this reason, we decided to develop a statistical attribution method to determine the origin of the change point. The idea of the attribution is that we use the data from the nearby station. So let's say with the nearby station, we have two additional series, G prime and E prime. Combined with the two series in the main G and E, we can form 6 series of the difference. And then we test the change in the mean in each series of difference. From the 6 test results, we can predict where the change point comes from, thanks to the logical table. So for this example, you can see that the first 3 series involved by G have the quite obvious downward shift. We say they have this significant result denoted by -1, and the last 3 series have no change, so denoted by 0, insignificant result. From that, we can say the change point is due to GPS, not error. And to do that, I would like to introduce how we construct the logical table. When we do this, we encounter 2 problems. So what I do here is to list all the possibilities we can have in the 4 base series, main and nearby. And then in total, we can have 54 configurations in the logical table. The first problem is that sometimes we have the same in the truth, same result in the logical table from different cases in the truth. You can see in this, for example, in the yellow line, the first one, we have the 2 positive trend in the G and G prime. And the second, we have the negative trend in the E and E prime. And they give the same result in the logical table. So what we do in this case is that we adopt 2 fundamental rules to have to compute the probability of each configuration. And this is prior probability. The first rule is that it is less likely to have the same change point in both main and nearby station. And the second rule is that it's more likely to have a change point in E and E prime at the same time because they're operational. So after remove some configuration by probability, we have 46 configuration. And then there's sometimes we can have some value in the logical table, which is 2 and -2. But the significant test can only give us the significant or insignificant result, 1, -1, or 0. So what I do here is to truncate, to do the truncated table. What I do is just to change 2 to 1 and -2 to -1. And after remove some duplicated cases, I have at the end 38 configuration. So here's is one example of the, so here's our full logical table used in the attribution method. So now I want to introduce how we make the test and construct the prediction. For the test, we follow the regression approach. So the time series also model with the mean, the jump, and the seasonal bias, and the error. The error here is we model taking into account the heteroscedasticity in the noise and also the autocorrelation. So we model the autocorrelation by the autoregressive moving average 1-1 noise model. And we use the feasible general line least square to estimate parameters, the variance of the parameters. From that, we can compute the test statistic and test the null hypothesis that the jump as the change point detected by the segmentation is 0 or not. The test statistics are equal to the estimate of the jump divided by its standard error. For the prediction, our idea is to use a classification to classify the test results into different configurations. So the traditional approach is to train a classifier is like this. We have the label data. We divide it by, we separate by the training set and the test set, and then we train the classifier on the training evaluated in the test set. But in our application, we cannot do that. We have no label data. We don't know what is the true configuration. And another problem is that some cases, some configuration we don't expect to have in the real data. And indeed, they don't, not very frequent in the real data. For example, for the case when we have one change point at the same time of 4 series, so it's quite rare. So what we do to solve this problem is that we construct a synthetic label data set using the resampling technique. And here is our proposed approach. With the test result from the real data, we separate into the train and test set, and then we make the synthetic data set with a label with the help of the resampling method and the logical table. We try to train 4 different classifiers, and we found that the best classifier is from the random forest approach with the smallest misclassification error. So next, what we do is to apply the classifier from the random forest method to the real data. And when we have more than one nearby station, we will do the aggregation of all nearby stations with the help of the prediction score. So in this, to compute the prediction score, we can do the weight for the different nearby stations. And in my study, I compared 2 different weights. The first one is become from the prior probability from the logical table, and the second is inverse of the distance between the main and the nearby station. So in my presentation, I will show you the result when we apply the prior probability weight for nearby station. So first, I show you here the result before the aggregation. This is the count of the number of cases for each configuration. So first, this is the result from the repro 2 data as the main data, and we use the repro 3 as the nearby data. So for this result, I trained the classifier on 500 sample. And you can see that there's many cases not in the table, which is indicated by the green color in the bar here. And in the first look, we think this result is quite aligned to our expectation. So there are some high probability configuration we expect here is that the configuration 1, 15, 23, 31, 35, they are all high probability as we computed in the logical table. And currently I am working on training a better classifier from the bigger data set. I try with the repro 2, repro 3, and with the 600 main station, I can run this classifier on 13,000 sample. And you can see here that the trend is quite similar to our result, with high probability on the configuration 1, 15, 32, 33, 31, and 35. So that's what we expected. After aggregation, we compare the result between the two data sets, and we see also that the largest portion are attributed to the GPS data. Some of them are attributed to the E and E prime, which is reanalysis data. And we have a big group, a small group here with the G, E, and E prime. It's a little relatively smaller when we apply on the repro 3. And after the aggregation, we see the impact on the trend estimate. So here I compare the result of the trend between the GPS NGL repro 3, and here the results come from 410 stations, which are fully homogenized. And I compare it with the era 5 analysis. So before the homogenization, we have in the red point, and after homogenization is in green. And you will see that after homogenization, value are better aligned to the era 5. The mean trend also closer to the era 5 after homogenization. And the interesting point is that after homogenization, we get a more significant trend. Here I show you two examples. We can see all the results from the segmentation, attribution, and trend estimate. So the first example here, you can see that we have three change point detected by segmentation. One is very big, around 2005. And all three change points here are attributed to the GPS. So after the correction, we have the trend is much smaller than before the correction. It's opposite to the second example, where we have also three change points detected by the segmentation. And after the correction, we see that the trend much higher than before the homogenization. So that's what I have in this presentation. To summarize, I would like to conclude that our homogenization methods can correct the jump in the interrooted water vapor time series and bias in the trend estimate. So in this presentation, I talked about two important points in our homogenization. The first is the segmentation, which automatic detection of the change point in the heteroscedastic series. And our team have already implemented this method to the R package, namely GNSS and GNSS Fast, which is the faster version of the GNSS. And for the attribution of the change point, our methods can couple with any differential segmentation method. And I also implemented this package, namely GNSS Arch. So currently we are working on implementing the full homogenization package, and we hope to have some review from the user. Thank you for your attention, and don't hesitate to ask me any question.
Thank you very much, dear Ninh, for your very interesting presentation and the interesting results you have shown us. Well, I don't have actually questions. Everything I wanted to ask, it was done in Paris in December. So I would like to ask our colleagues from the audience if they have Any question to Ms. Ninh? I cannot see anything in the chat. I mean, please feel free to. Yeah, there's a question from Izsák Joseph. What is the definition of nearby station? What were the criteria to select a nearby station?
Yeah, thank you for your question. This is very for now we look for the nearby station with the criteria of 200 kilometers, because sometimes we have very spare network, but for many GNSS stations we can have 10 or 20 very close nearby station. So to compromise between the number of cases we can test and the distance, the quality of the test, we select 200 kilometers.
Okay, thank you, Ninh. Izsák, you're covered with this reply? I think yes. Okay, thank you. Any other question, please? No? Okay, then, Ninh, thank you very much again. I would like to thank very much our two presenters of this afternoon, Ninh Nguyen and Beatrix Izsák. Monica, you're still with us, I think.
Yes, yes, I'm here.
Am I missing something? Can we conclude?
First of all, I would like also thanks all two presenters showing their results and share with this community. And thanks to Tanya's hosting this event and chairing this session, and also to the whole organization committee keeping going this serial. It's very important because I'm representing here not only the homogenization community, but the UMetNet climate program. And this program, we are very committed to keep going this colloquia, so this online event. And I also would like to encourage you to propose presenters for the next event, which will be expected in autumn, if the committee is agree on this. And also, if someone is not on the homogenization mailing list, just drop me an email. So my name is lakatos.met.hu.
Monica, can you enter it in the chat?
Yes, I will enter it. So the Hungarian Meteorological Service is maintaining now the homogenization mailing list. So I write it into the chat soon. So that's it. That's it. So please distribute this opportunity to get informed about the news on the homogenization issues, and please think about contribute to the seminar and also propose. I also wanted to say that Xiaolan Wang finally had to cancel her presentation, but we will invite her again for the next occasion.
Okay.
So thanks for all joining us. Thank you.
Yeah, Peter, you want to say something?
Yes, do you hear me?
Yes, loud and clear.
I would like to offer a presentation for the next event.
So we will discuss. Okay.
Thank you very much, Peter. Yeah.
Okay, thanks. Should I say now more, or we will discuss with Monica Itanos?
The organizing committee will contact you as organizing committee
Yes,
for
yes.
the details, but this
Okay.
will be done later on because the next colloquium will be somewhere in autumn. We will define it later on. Thank you, for proposing to participate actively. So Monica, I'll send you the recording of the today's conference. You'll be able to distribute it through the HumanNet page, I suppose.
Yes, yes, and we will share you the link for the whole community, not only the HumanNet one.
Okay, so thank you everybody for being here this afternoon. I wish you all the best for the next days and for the summer holidays, although it's a bit soon. And we'll be in touch either individually or via the homogenization mailing list. Thank you very much again for presenting, Ninh and Beatrix. Okay, goodbye everybody.
Thank you. Bye-bye. Bye-bye.
Goodbye.
Thank you. Bye bye.
Thank you.
Bye-bye.